चालू हो गया स्ट्रीमिंग। स्टार्ट करते हैं सर।
ओके, कितने लोग हैं अभी?
मैं बस लाइव हो गया सर। मैं स्टार्ट
चलो
करता
शुरू
हूँ बाद
करते
में आप। Welcome everyone. Thank you for joining us for today's webinar. My name is Ankit Kumar Patel. I am the head of Department of Aeronautical Engineering at PITDS Parul University. Parul University is the leading provider for innovative graduates. Today we are presenting a webinar titled as Space Material, Present Tense and the Future Perspectives, presented by scientist Ravi Verma. Just a little housekeeping before we get started. If you have any question during the presentation, please type them to my number. My number is 9978225359. I'm repeat again, 9978225359. I will bring them up during the presentation, and we will also have time for the question at the end. Now, without further ado, we will turn the time over to scientist Ravi Verma with a great knowledge and expertise on the subject. Yes, sir.
Thank you, Ankit. Thank you for inviting me to deliver. Thank you for inviting me to deliver the lecture at Parul University through webinar. So today I'm going to talk about in which actually field I have learned near about foot. I have worked near about 14 years in ISRO. Just 1 second, I will load my presentation. That is visible, Ankit?
Yes, sir. Yes, sir.
And audible, and then voice is also audible, na?
Yes, sir. Yes.
Okay, then. So, once again, welcome to each and everyone who is actually right now attending my lecture. And as Ankit mentioned that since last almost 13 years since I am working in ISRO. So initial I was working in a rocket technology, means Vikram Sarabhai Space Center, which take care of all rocket related activity. And for past 6 year, I was working in a space application center and take care of materials. So entire 14-year career actually I spent near about to testing and qualify and providing a reliable space as well as aerospace material, so that a mission, or you can say the intended use of a material should be performed flawlessly. So today my topic of discussion or presentation is basically space, aerospace as well as space material. The present and trends means what right now we are using, and what is the next future course of action, means what is the future perspective that we are going to use for next 30-40 years. And I hope you will enjoy. So before going to detail for material, just a snapshot of ISRO activities, because what happened, most of them is basically understand what actually ISRO is doing, but to be just emphasize or just precisely what actually we are doing. So basically ISRO is formed in 1963, none other than Dr. विक्रम अंबालाल साराभाई. साराभाई मीन्स अंडरस्टैंड के किसी के नाम के पीछे अगर भाई लगा मतलब गुजराती होगा. So Gujarati initiated the space activity in India. He belongs to Ahmedabad, Gujarat, and he only sits, or you can say initiated the space activity in India. Started from TULS, Thumba Equatorial Rocket Launch Station, Thumba. Right now it is situated in Trivandrum. From there we started from the modest beginning, and we started from a sounding rocket, and slowly we have understand the complexity of space. And after that we are mature enough to put our own satellites as well as rockets in the space. So the main purpose, if you see overall, the main purpose of vision behind ISRO is basically we are second to the none in the use of the application of the advanced technology like space technology to the benefit to the common man in society. So still, so more than 50 years is over for this organization, but the main purpose or main goal of this this organization is basically how you can play a meaningful role for the development of common man as well as the our people's society. That is the main purpose behind the genesis of ISRO. And if you go to in detail what are the bifurcation of space activity, or you can say Indian space program, so we have near about 6 wide category in which we can bifurcate our ISRO activities, in which most of them applications basically application oriented. It means space application means the satellite images what you are getting, or the information what you are getting from satellites, it may be useful, it will be useful for the common man like farmers, agriculture, for agriculture purpose, for forestry, for environment, for ocean, for ecology, for meteorology application, for defense, strategic application, for resource monitoring. So there are a number of application of space technology. So there is a one bifurcation, or you can say the category of work is basically a space application. Second one is satellite communication. It means based on the communication satellites, which means the 24/7, the application is basically 24/7 into 365 multiplied the applicable life of the satellites, which can be used for your TV broadcasting, D2H direct to home, meteorological application, strategic application, ocean monitoring, etc., etc. Third comes launch vehicle. If you want to put any satellite in the space, so you have to be launch vehicle. You have the capability of certain kind of capability, or you can say have such kind of rockets or satellites, or rocket or launch vehicle. They can come and they can put a satellite to the specific or desired orbits. So this is also one of the category of ISRO working area. So basically launch vehicle, satellite communication, space application. We have a satellite navigation also. This is the actually category, you can say last 10 years included in ISRO activities, which provide the actual application like your GPS is there, but it is called IRNS. It is not the global, but it is regional. It is called Indian Regional Navigation Satellite System, IRNS series. And in short form, it used to be called NAVIC, NAVIC, Navigation with Indian Constellation. This is also used, and this is main application is basically to provide the actual positioning, time, positioning, and accuracy of a positioning. Same time, there are so many strategic applications for these navigation satellites. Earth observation, we have the you can say the vast legacy of remote sensing or Earth observation satellites, which is started from Bhaskara and Aryabhatta, and right now we are going for a CALTO series of satellites, and the resolution is started from some few kilometers. So right now we are going for some millimeters. So this is the actually vast you can say advancement or the newer technology or latest technology included in remote sensing, which capture the images of Earth and taking real-time information with respect to your resource monitoring, environment, ecology, forestry, etc., etc. So there are vast variety of ISRO application, whether it is launch vehicle, whether it is communication, whether it is navigation, whether it is Earth observation. And we have one more category, it is called space exploration and space science, which take care of the interplanetary exploration. It means other than Earth, we have the different planets in our solar system. So we want to explore what are the possibility of life on the other planets, as well as what is the usability of explored meteoroids, as well as what is the feasibility to explore the other planets. So right, so we started this activity in 2000, way back in 2008, launching a Chandrayaan 1, 2013 Mangalyaan 1, 2019 Chandrayaan 2, and now we are planning for a Mangalyaan 2, Chandrayaan 3, Venus, as well as Aditya. So these are the mission in the pipeline to explore the different planets of our solar system, and to understand the formation of life and the usability of other planets or other you can say celestial body, how they can benefit it, or how can best extract the resources or minerals or the energy which is available on the other planets, so that in future maybe habitat of life can be possible on another planet that can be utilized. So as I mentioned in my previous slide also, if you broadly categorized, so mostly the Indian space program is basically throughout the journey, throughout from 1963 to till 2020, is basically the main vision of Indian space program is basically shared, nurtured, enrich the Indian space program over the decades. so that the main purpose is basically a pupil centric, or you can say application driven, and how to effectively utilize the Indian space program for a benefit to the common man. And as I mentioned in my previous slide, we have the variety of application in which just one second, in which we have the in which if you go to space application point of view, means what are the application of space technology. So we are basically this application of technology we are using for the betterment of common man. It means it is actually used for agriculture and forestry, weather forecasting, disaster management, oil and gas, geology and minerals, civil aviation, broadcasting and DTS services, and VSAT services. So this is the main application, especially from the space technology point of view. We have a space infrastructures. It means to to execute the space application, you required some infrastructure so that the connectivity can be easily connected to the end use, up to the end use point of view. So we have the communication satellites, we have the Earth observation satellites, this is called remote sensing satellites. We have the navigation satellites, it is called RNS or NAVIC, and we have the space science program. For capacity building, it means we have the technology development, we have advanced R&D, infrastructure and facility, indigenization of industries, and the human resource and skill development, because this is also one of the most important criteria to sustain any organization. If you want to successful in a competitive market, you should have a advanced R&D as well as skilled human resources and skill development. And at the same time, since the space is basically strategic and advanced sector, and the most of the things is basically we used to procure from outside, from a foreign exchange. So most of the thing you have to indigenize, means it should be developed inside the country or by Indian vendors or Indian industry. So that is also one of the prime activity, how to indigenize the space activity in India. And the same time, space transportation, we have the legacy of the launch vehicle, which start from SLV3 from 1970, 81 on 90, 70, 80s. That SLV3, its project director was none other than late Dr. APJ Abdul Kalam, the former president of India. And after that, ASLV, augmented satellite launch vehicle, early 80s and 90s. Then now, at present, the workhouse of ISRO is basically PSLV, Polar Satellite Launch Vehicle, which is used for launch the remote sensing satellites up to 1.5 to 2 ton in the remote sensing or a sun synchronous orbit. We have the GSLV Mark II and Mark III, or in the short version, you can say GSLV Mark III 1, 2, or you can say Bahubali 1, Bahubali 2, which can carry a satellites in a geo orbit up to 36,000 kilometer for 2 ton to 4 ton. And after that, we have the advanced we are planning for RLV, like a space shuttle. It is called reusable launch vehicle. And planning for an in future, we are planning for a Gaganyaan to send at least minimum 2 to 3 astronauts in a space for 3 to 5 days. So such kind of activity actually ISRO is doing, and in future we are going to plan it in a better and advanced way, right? So in all these things, if you talk about ISRO activity or application point of view, so the basic purpose, or you can say vision or genesis of ISRO, is basically harness the space technology for the national development. This is the genesis of ISRO, and that is the vision of ISRO, to harness the space technology for the national development in terms of common man, or utilization of space or advanced technology for the common man. But I mentioned that this all technology, all the things, even though I am talking about application, launch vehicle, satellite, remote sensing, navigation, geostationary, or communication satellites, right? All the things, when we talk about this, there should be something which has to be started. It means it has to be done in a physical way. Physical way means it has to be made by some materials. It means the selection of material is very, very important. If you talk about space material, whether it is aerospace, either be your helicopter, fighter jets, or you can say missile technology or rocket technology or satellite technology, anything, if you want to make a physical thing, it has to be necessary built by some materials. So the selection of material is one of the most, you can say, crucial or critical criteria to understand, because if you not understand the integrity of that material, then you may be in the soup in the future, or maybe in between you may face so many problems. So that's why the selection or the or the elements of Indian space program basically started from the evolution of materials. Now, if you go back to your history, any material, any material means if you talk about any material, or if you talk about any civilization, whether it is Sindhu Ghati Sabhyata, Indus Valley civilization, or Mishraki Sabhyata, right? So we used to call our all the civilization from rivers. It start from rivers, but at the same time we bifurcate our civilization based on their development of material also. Because if you remember, we started our civilization from Stone Age, then Bronze Age, then Iron Age, then Synthetic Age, now Intelligent Age, and we are planning for a new artificial intelligent AI age. So so even though civilization bifurcated based on the different factors, but one of the criteria for bifurcation of civilization is basically selection or the advancement of the material also. So that's why our evolution of material start from the Stone Age, and slowly we come to understand the material technology or metallurgy point of view, and we understand the making of material, forming, forging, or shaping the material. So started from Stone Age to Bronze Age to Iron Age to Synthetic Age. Right now it is the Intelligent Age. Right now we are living in the Intelligent Age, but future is basically a space shape memory age, or you can say artificial intelligence material, or the Intelligent Age will come. And these actually bifurcate your cost of living as well as your civilization. So it is also one of the criteria to bifurcate or divide your you can say your civilization. So you understand now, you can understand how the material is basically critical from for aerospace point of view or space point of view. But if you talk about specific from space, so we used to talk definitely what are the factors which affect the selection of any material for the space as well as aerospace application. So if you talk about space means I can bifurcate approximately near about 70 to 80 kilometer, and normally space is started. But if you go to above that, you are facing so many problems because you are crossing the atmosphere. So if you are crossing the atmosphere, there are so many problems encountered by satellite as well as the object which crosses the atmosphere. One of them is debris. Debris means the material which is the things which is right now not in use, or which is not actually applicable to or which is not a functional applicable to any requirements. So these debris also create a problem. So the selection of material also based on the number of debris. Extreme temperatures. Extreme temperature is also one of the prominent criteria for selection of any material, because in the daytime when the satellite is actually in front of sun or daylight, it maybe comes around the temperature up to 152 plus 200 degrees Celsius in a daytime, and the same time either be during eclipse or the portion at which sunlight is not there, it maybe comes near about minus 150 to 200 degrees Celsius. So in a span of 24 hours, the material or maybe the satellite which is made of materials, it may you can say vary from plus 200 to minus 200, means overall 400 degrees Celsius variation during 24 hours. This is also one of them you can say crucial or the impact on the selection of material. Charge particle, we have the charge particle also, because this charge particle also play a very significant role for our very significant role, because in atmosphere they normally form in the gaseous form or a solid form, but when you go to the in the space more than 100 to 100 kilometer where the atmospheric pressure is not there, so they usually comes around in the form of charge particle. This O2 may be O plus plus O minus minus, H2 may be H plus H minus. So these also create a problem for the material, so that the material, because of that material erosion, corrosion, and different kind of problem encountered, and they start degrading or start degrading its own property, or maybe losing its property. Zero gravity, this is also you can say this is also one of the selection criteria, because because deep vacuums are there, so gravity is almost, because as you go to up, gravity will be slow down, or it will be decreased, and based on the square root of that. So it's also one of the criteria for selection of any material. Other than radiation, being since there is no atmosphere, so directly the material will impinge on the sunlight, and the radiation effect means the infrareds and other UV ultraviolet rays of sun will interfere with directly to the property of a material, and it may be create a problem for selection of any material. So it may be the possibility of material may lose the property in the environment, irradiation environment. Deep vacuum, since the negligible atmosphere is available, you can say there is no atmosphere, so deep vacuums are there. So in deep vacuum, so many materials are losing their property, and same time the magnetic field. So these are the criteria, or these are the factors which affect the selection of any material for the space as well as aerospace material. So while you are selection of material, or while you are selecting any material, you should be think such kind of property which is very critical of selection of any space material. At the same time, it should mitigate, or it should be meet all the requirement as desired by its functional requirement, so that is the functional requirement should not affect, and same time is meeting all the requirement as applicable to mitigate the problems and effectively for the lifetime. For remote sensing, it may be 5 to 7 years. For communication, it may be 10 to 12 years to perform satisfactory, and the same time without any hassle or you can say problem. So when you understand okay, these are the problem material is going to encountered, so there are the property, then the inherent property of individual material comes into picture. So while the application, when you understand the application requirement of any material, so there are the wide variety of, you can say, the property of a material that comes into mind, and based on your requirement you have to choose the optimum material which meet your requirements. It means when you are selecting a material, you should think strength, means whether it is used UTS, means ultimate tensile strength, or YS, yield strength, percentage elongation, its weight or density. Stiffness means load divided by how much deflection comes based on the load, stiffness. Toughness. Creep rate means strength sustained by the temperature effect. Wear, during the time here wear and tear problem comes. Thermal environment, thermally all the satellites actually has to be mitigate the thermal environment, because as I mentioned that daytime plus 200, nighttime minus 200, and inside the electronics which is working near about 35 to 40 degrees Celsius. So you have to see that the outside temperature should not interfere the functional requirement of electronics which is actually working on 35 to 40 degrees Celsius. So though you can say proper thermal treatment or thermal balance for any satellite is very, very crucial. And if you are not maintaining proper thermal treatment, so then the satellite life will be reduced, or it may be happen that the satellite will actually perform malfunctioning and maybe stop working also. So these are the factors which actually govern the selection of any material, which include strength, weight, stiffness, toughness, creep rate, wear, thermal impact, lifetime, hardness, fatigue, electrical, optical, magnetic expansion means thermal expansion, means coefficient of thermal expansion, flammability, melting point, corrosion, erosion, machinability, weldability, glowability, toxicity, finishing, n number of parameters are there. It means when you are talking about the application requirement, there are n number of parameters. All parameters you have to see whether the material is not going to interfere any application and any other material, or thermal point of view, electrical point of view, magnetic point of view, fatigue point of view, life expected life of maturity, flammability point of view, melting point of view, glowability point of view, glass transition point of view, glowability, toxicity. Because when you talk about human space HSP, human space flight, or maybe Gaganyaan project, in which the human are going to survive for 3 to 5 years, or maybe future if you are going for ISS type, it means International Space Station type, so where people are living for years. So you should not have the flammability or toxicity, because human life are involved. So material should not inflammable, viscous, or toxic, so that fumes may create a problem for survival of the humans. So selection of material is basically one of the most crucial thing to initiate any space activity. And these are the some of the point. This table or this requirement may be n numbers based on the requirements. So some of them actually I have highlighted, but other than also some of the parameters which is also useful, like material cost, availability, interaction with other materials. This is also one of the most criteria, like interaction with other materials. You are selecting on one material, and it is going to be weld or rivet, or maybe its application will interfere to other material. It should not be interfere the property of another one, such as one material magnetic property or electrical property should not interfere with another magnetic property or electrical problem, because otherwise the EMF, electromagnetic induction, or such problem will arises, and it create a problem. Same time, your fuel, let us suppose N2O4 or N2O4 or different kind of fuel we are using, like solid, liquid. There are so many fuels we are using. So so this fuel, if it not compatible, if it is not compatible with your material, so it may be create a problem. So while you are selecting for a propellants, so you are making that, you can say, tank, so the tank should be compatible with your propellants, so that the requirement of propellant should be made by that particular material. Otherwise the interaction create a problem. And same time, in space there are so many problems in Scotland, so you have to see that whether the material is, whether it is a coatable or paintable, or it can be used by as it is, or it may be annealed one, or it may be in terms of process or enhances surface capability. So while selection of any material, especially from space or aerospace sector, you have to broadly sense and think about such kind of application requirement, as well as availability, material cost, and interaction with material. And availability of material cost come into picture, because when you are going to take the material outside, we are taking so many material from the outside in the past, but slowly we understand it will actually impact on the our space program, as well as the schedule of the particular mission and projects. So that's why we started the indigenization activity, and based on the Indian vendor and industry, we try to develop. And right now we are capable enough to develop near about 95% of the satellite as well as rocket material are indigenized. It is done through Indian industry, so that we have saved so much foreign exchange, as well as to meet our critical schedule, to meet the desired requirement of nation development in terms of space technology. This is one of the you can say very famous Cosby diagram, in which while you are selecting a material based on their Young modulus and density, because this is also once you are selecting a space material, you have to think that the material should have the high strength, but the density will be less, its weight should be less. It means less weight and strength is high. Such kind of material is usually preferable while selecting any material for space as well as aerospace. Either be it's aeroplane or a fighter jet, or maybe satellite, or maybe launch vehicle or satellites, it is always applicable that the material which is used or which is used for fabrication should have high strength as well as less density. And this shows that what are the different kinds of material in the different regimes are there, what are the density kg per meter cube is available, and same time what are the strength, especially in the Young modulus, what are the things. And based on this diagram you can easily select whether I should go for a metal, I should go for a composite, I should go for a metal composite, I should go for a carbon composite, I should go for a wood, or I should go for a foams, polymer, rubber, metal, alloy, or alloy. So there are so many different kinds of metal we are using. In terms of broadly sense, we are using near about 350 different kinds of material, started from launch vehicle to satellites. It means we have the variety of material which started from your foam or maybe adhesive to the high strength alloy steel like maraging steel or other steels are there. Titanium, maraging steel, 15CDV6, such kind of steels are there. So I can say approximately near about 350 different kinds of different category of material we are using in launch vehicle as well as satellites. And we are going to talk what kind of different main elements we are using. But I mentioned, when you are talking about material, talking about the space material, one problem used to come for indigenization or challenge development is basically material development and challenges. Because when you are indigenization through Indian agency, so selection of material is basically involved a simultaneous consideration of number of diverse factors, and the diverse factors I already mentioned, whether is strength, density, toxicity, glowability, and interaction with other cost, coatings, n number of parameters are there. So these all parameters you have to think while selection of any material. Same time, the material fulfill all combination of conflict requirement and meet the severe environment condition for the mission demand. As I likely mentioned, any mission, whether it is going for a remote sensing up to 700 to 800 kilometer, or maybe the geostationary 36,000 kilometer, there is a space, there is a severe environment. Severe environment means since in space there is no air, right? Deep vacuum, and since no air, that's why there is no maintenance. So there is no air, so no maintenance, so you cannot repair it. It means no air, no repair. And when you no repair it, it means you have to, while selection, you have to be test and qualify all the things on the ground, so that the worst case scenario can be predicted on ground, so that at any point of chance you should not miss any chance to fail or malfunctioning of any individual component or product. So that's why while you are selecting any material, you should meet all the conflict requirements of your selection requirements, and at the same time your material or job project or job should meet environment condition, and the same time meet the functional requirement up to end use, up to its predicted life. And third and foremost, ISRO has made the concentrated effort for indigenous development of all the materials, their processing technology, and productionized them to the industrial level using the existing nature. This is the main point that I am want to highlight. Most of the material, as I mentioned, or near about 95% of space material is basically indigenized through Indian industry, and right now we are self-sufficient in terms of space material. They can be easily procured, built, or you can say design, development, and making, casting, making, shaping to any form in India is possible. And these are actually you can say concentrated efforts of the ISRO scientists as well as the metallurgists, especially in terms of metallurgists. But when you are talking about materials, so material for the space environment, what are the things while you are considering a selection of any material? So for space, because right now we are talking about the what are the ISRO role, what are the selection criteria, if you want to select what are the problems encountered, but what are the problem actually happen to the material, that we want to highlight. Because when you go to the space, you are facing a problem like degradation of the radiation and thermal cycling, because as I mentioned, minus 200 to plus 200 degrees Celsius day to night time. So because of that, thermal cycling means changing in temperature in 24 hours is also degradation, and because of radiation this problem may come. Second one is presence of atomic oxygen. As I mentioned that for a low earth observation or low earth orbit, you used to face the problem of nascent oxygen, or you can say atomic oxygen. Sublimation and evaporation of the high vacuum space, since there is a high vacuum which is 10 to the power minus 12 torr or more than that, so there is a chances that most of the polymeric material have the problem with sublimation and evaporation. So that is also one of the selection criteria, or you have to think while selection any material. Cold welding in the friction atmosphere, since there is no vacuum and high vacuum, deep vacuum condition in the low temperature, there is a possibility that if the cold welding or friction welding can be automatically started in itself in the materials. Sub-zero condition during solar eclipse period, as I mentioned, solar eclipse, there is a chances that material since there is no sunlight, so the temperature will be more than a 200 degrees Celsius in a minus side. So there is a problem with solar eclipse. High velocity particles, so there are so many debris available in a space, so that debris may impinge or maybe impact on your satellite or maybe the space object, and maybe create a problem for that. Use of SN, ZN, and CD may be avoided, because this zinc, lead, and PB, zinc, lead, these actually problem of contamination, and same time their nature is toxicity, so that always used to avoid such kind of material. Magnesium parts should be always plated or coated, because you have to stop the sublimation of magnesium, because magnesium sublimation can be started in the normal temperature also, and it's very fast that it will be eroded or corroded. So it's better to have the magnesium parts should be plated or coated, means properly protected. Or FCC means phase centric material should be used in the cryogenic application. FCC means phase centric material should be used, because they have the very good resistance to ductile to Beaton transformation. Because what happens, most of the material when they are using in the high temperature as well as low temperature, whether it is a high temperature or whether it is low temperature, most of the material which is very good in the normal temperature, they are losing their property in low and high temperature, and they react like a brittle material. It means the steel which is let us suppose 500 megapascal strength in a normal room temperature in like our normal environment, if you are putting a same steel in minus 200 degrees Celsius, it may be broke like your chalk. Like you understand a chalk, it can be break like chalk. So even a steel can be easily broken by the low temperature. So you cannot predict if the material which is having the normal room temperature property is very good, the same property can be sustained by that material low as well as high temperature. So that is also one of the selection criteria for any space material. So while selection of any space material, these are the very important point that you have to consider while selection any space material. So that's why when you are selecting the space material, but at the same time while you are selecting a aerospace material, aerospace means the material normally used for the aircraft structures, your spacecrafts, right, your launch vehicle, missile, as well as your jet propulsion, or maybe the jets, fighter planes. So one of the main best criteria for selection of such kind of aeroplane, or maybe the flight is basically high strength to density ratio. It means its strength should be high, but the same time its density should be less. It's called basically specific strength of that material. It should be very high. Second thing, high lasting modulus, but the same time density ratio should be less. It means specific modulus. So while selecting any aerospace material, you should have the high specific strength as well as high specific modulus of any material. Same time, adequate fracture resistance. Fracture resistance means we usually consider a material is basically homogeneous in nature. We consider material all directional property, all direction is almost same, but in practical all material is not homogeneous. They may be heterogeneous in nature. Same time, it doesn't mean that every time a material should possess a property in all directions, same property. It may be possibility that different direction material having a different properties. So at the same time, we are assuming that material having a don't any defect, but you understand every material during the processing there are some chances of defect. So whether the applicable size of defect can fulfill by functional requirement, that is the main point of consideration during the fracture toughness design. So that is also one of the criteria while selection any aerospace material. Easy fabrication and easily vendable. Machine should be easily available, easily machinable, easily heat treatable, and easily weldable. Compatibility with other materials, it should not be interfere the property of other adjacent materials, nearby materials. Adequate strength for high temperature as well as low temperature. As I mentioned, high and low temperature material should possess the same property, so it should not lose its property in high as well as low temperature. Effective quality control, and as I mentioned, cryo application D2BT means ductile to brittle transformation should be avoided, and easy availability at reasonable cost. Otherwise, even though material may be having a possess a good property, but since it is very costly or availability is difficult, so that cannot be considered while selection any material. So these are the point that you should consider while selection of any material. So this is basically criteria for selection of any aerospace material. So right now we understand what are the selection criteria for space as well as aerospace material, and there is a different bifurcation of materials are there. We are using a wide variety of materials in space as well as in terms of launch vehicle spacecraft, right? But in general, we are using different kind of materials. So I will talk upon which material which normally we are using at our spacecraft application, which is AISI 304SS, stainless steel, aluminum 6061, magnesium alloy AZ31B, Invar, which is Fe nickel low expansion alloy, super Invar Fe nickel, once again the expansion alloy but very low coefficient of thermal expansion, Kovar Fe nickel cobalt based alloy which is having a very good strength as well as thermal conductivity, phosphorus bronze, brass, beryllium copper, silicon carbide, CFRP, and zero door, etc. etc. We are using in launch vehicle like 15ZDV6, Maraging steel, titanium alloy we are using in a launch vehicle also. So we are using a variety of material which start from the adhesive to the high strength carbon alloy steels, or you can the composites, based on their variety and application, based on their requirement, functional requirement, variety, application. We are using a different category and different types of material in a different location and position of it. But while selection of any material is basically you have to test and qualify. So the basic purpose for any material selection is basically depending on these 4 parameters, like what you want, it means performance, what actually you want, or what is your desirable output, or what actually desirable requirement from the any material. The performance, you have to select the best structures material, what are the type of properties inherent by material, and the processing, what are the processes is involved. So while selection any material or to test and qualify any material, you have to see the structure, properties, manufacturing, and performance. These are the four parameters, is basically main four pillars of any successful selection of any material. And while the selection of any material basically depending on the different kinds of tests involved, which may be stating in the nature like tensile, like UTS, YS, percentage elongation, bending and fractional, 3-point bending, 4-point bending, to understand the fractional requirement. Basically, this is test used for ductile brittle materials, compression, creep and stress rupture, torsion, right? Hardness, impact, fatigue, isothermal, as well as fatigue, thermomechanical, plane stress tension, plane stress compression. So these are the tests is normally preferable for selection of or testing of any material, especially from the mechanical point of view. Other than fracture point of view, we want to take it K1C, J1C, like CTOD, K1C, J1C, CTOD. There are different kind of dynamic testing in which you are simulating the actual environment in which your material is going to be going to be sustained. Mostly such kind of material used in the turbine jet propulsion, where high temperature, high speed fuels are high applications are there, in which the rotation which high speed and high temperature is required. So the material should sustain its life up to predicted time. So such kind of tests are required to test and qualify to fulfill the requirements of functional requirements. Environment and climatic tests like humidity, thermowake, thermoshock, means thermocycling, thermo vacuum test. Other than that, we have the thermal conductivity, peel strain adhesion test, lab shear test, outgassing, peel strain, CT, means coefficient of thermal expansion, and space radiation test. One thing I want to actually emphasize is outgassing test. Normally in the room temperature, polymetric material don't show any outgassing or off-gassing. Outgassing means naturally emission of the inherent gases of the material, and off-gassing means you have to forcefully take out the gases from the material. There is a difference between outgassing and off-gassing. So outgassing is one of the most important test parameter for selection of any space material, because most of the material having the capability to outgas the property at the low vacuum as well as high temperature. So we normally used to test all the material is high temperature as well as high vacuum and simulate the testing conditions. So we simulate the testings through outgassing testing at our lab, and we will test and qualify most of the polymetric material which is going to use for our spacecraft application. Because what happened, if you're not test is outgassing property, it may be chances that during the course of you can say time inside the spacecraft, your material may start outgassing, and these emitted outgases may be deposited or may be condensed on your circuits or carrier plates or maybe your PCB, and it may be that they can jam, or you can say they can stop functioning, and it may create a problem. So that's why all the material which is used for spacecraft application has to be tested and qualified in outgassing. As I mentioned, there are different kinds of or category of material. So I will talk about, let us suppose PSLV. So from first stage we are using like 15CDV6 and maraging steel. Maraging steel means motor case is made of maraging steel, that is called PS1. M250 maraging steel. We have a 15CDV6 for a strap-on. We have a 2014 interstage. We have a F-Note 7020 for the propellant tanks. We have TI6L4V titanium for our PS4 housings. We have magnesium alloy for keeping our avionics systems. We have 7055 for our heat shield application. So we have the variety of application from launch vehicle from first stage to fourth stage in a PSLV. So these are actually in a broader sense. Other than there are so many materials are there in a launch vehicle, but to just emphasize, different category of materials are using for different application, and based on their functional requirement, specific requirements, there are different categories of material which may be steel, aluminum, titanium, magnesium, or different category of material based on the strength, specific requirement, density, thermal conductivity, etc., etc. So this is the actually broader sense of PSLV. In the same manner we are using in GSLV Mark II, same way like maraging steel, for our PS1 motor case, L40, which is made of 7020 aluminum 7020 or L40. Our brace shot is made of 2014 aluminum A2014. Interstage once again 2014. And magnesium housing for avionics component, keeping avionics heat shield once again 7075. And titanium for interstage structure. Cryogenic tank is made of aluminum A2219. So different category of material used in the different stages. And this is the GSLV Mark III, which the rocket which carries our you can say Chandrayaan 2, last year Chandrayaan 2. It is also its total weight is near about 640 ton, means around 640 tons, and its total capacity to take a satellite in a geo orbit near about 4 ton. And it is also made of the different category of different materials, which variety of different materials used. And as I mentioned, if you talk about materials from spacecraft to launch vehicle to application, we have near about more than a 350 different category of materials we are using. So these are the some of the snapshot of this basically category of material. If you talk about structure material, especially in terms of launch vehicle category for space application, we have the primary requirement, as I mentioned, that we should have the high specific strength or specific modulus. Same, it means the per kg weight should be less, should be shaved up, so that we can enhance the payload capability or spacecraft capability. Because per kg, if you are putting a satellite in a LEO orbit, so per kg cost comes around 3,000 to 5,000 US dollar for a LEO low Earth orbit for remote sensing application. But the same time, if you're talking about the LEO geo application, means geosynchronous geostationary satellites, which is 36,000 kilometers far away from Earth, it costs near about $10,000 per kg. So you can understand that per kg material is how much charge to put a satellite or maybe to put a material into space. So that is also one of the selection criteria. You have to put a less amount of satellites or less amounts of weight, so that you can enhance the payload capability, or you can say enhance the performance of the payload, and you can do the desirable working based on the less cost, because cost also one of the prime requirement while selection of any material. High fracture toughness, easy fabrication, must satisfy widely config requirements, must be capable to face full hostile environment. It means all the hostile environment, as I mentioned in my previous slide, like debris, deep vacuum, zero gravity, magnetic field, charged particles, deep vacuum. All this condition has to be fulfilled by that material. Even ascending as well as descending node. As I mentioned, Gaganyaan, you are putting a human in the space. So while going to space and after the coming back is also good, even because going is not that much critical as compared to coming back, means descent entry. That is also one of the most crucial thing to come back to the space. And when you are come back to the atmosphere or come back to the Earth, atmosphere drag will create a problem, and the thermal degradation or thermal, and because of thermal energy, temperature reaches to around 2000 to 2500 degrees Celsius during the re-entry phase. And you remember that Kalpana Chawla re-entry, if you remember that, so you can understand what are the you can say predominant parameter while selection any material. Because while ascending you are selecting some material, while descending you are selecting some material. If it is not meeting both the criteria, you may be in the soup, or maybe you can lose the human lives. And as I mentioned, you can replace anything in terms of material, in terms of money, but you cannot replace a human life. If it is lost, it can lost. It means you cannot create a Kalpana Chawla second time. It means while you are doing such kind of critical and crucial mission in which your nation importance, prestige, same time the human life involves, you should not take any risk. You should be double sure it is meeting all the requirements. So that is actually one of the you can say responsibility for any material scientist as well as designer to select the proper material for proper location. Extending high demand of reliability, as I mentioned, it should meet all the you should be double sure. It means the reliability demand is very high, and same time it should be cost effectiveness, means operational phase it should be very cost effective. So to meet such kind of different demands, so not even a single material can meet all the requirements. It means now you have to go for such kind of material which can have the tailored property. Tailored property means like you are going for any tailor shop and making the cloths as per your requirement, as per your shape and size. The same way we can do such kind of thing in aerospace as well as space based on the using of composites, because composites, the main advantage, you can, it is a heterogeneous in nature. Its property can be tailored, and it's it's direct unidirectional. It means you can change the property based on direction. It means the longitudinal may be differ from transfers, may be differ from short transfers. So different direction, different property can be possessed by composites. So that is a very distinct advantage while using a composites. You have the high specific strength, high specific modulus, high thermal resistance, high electrical insulation, fire retardancy, and fire resistance, resistance to the chemical and corrosive environment. Directional property, as I mentioned, different direction, different property can be possible. Tailored property, complex shape, you can easily fabricate a different and complex shapes, right? Good fatigue life, acoustic insulation, and control thermal expansion, as well as RF transparency, means radio frequency transparency. So these are the factors which actually govern the selection of the composite, especially from the space and aerospace point of view. So while selection any material, especially for the tailored property, then composite always a good solution for anyone. And that's why this composite is always preferable to use in a good mechanical property as well as low density specific strength point of view. And these are the some of the product which used for a major satellite application, like in Carto Inset 3DR we have the cylinder, GSAT 70 we have the reflector, GSAT 19 we have the reflector, 0.7 feet antenna, different kind of antenna, whether it's phasor antenna or DRT antenna or solar panel. We have the different variety of composite we are using in a spacecraft application, and because of this we save the material as well as the weight of the spacecraft, right? We are actually different kind of tubes we are using. If you remember all, whether it is fighter jets, aeroplane, missile or rocket or any satellite application, we are using a different kinds of tubes. There are so many tubes are there in a different orientation and even a different location position, whether it is LEO, GEO, aircraft, it always actually enhance the signals. So such kind of tube, it is called traveling wave tube amplifier, TWTA. They are using in a tubes, and the main purpose of this tube, basically they are enhancing the signal, because from the ground you are sending a signal which is having a very low, then very low, you can say, strength. But when it is going to the tube, means from input to output, RF input to RF output, they will enhance the signal up to 8 octane, means increase the strength up to 8 times, and once again return back to the ground based on their application, because in the ground there are so many terminals to catch that signals. So that is the main purpose of tube, to basically RF amplify in the, it is basically a highly ultraviolet vacuum high device which actually enhance the RF, means radio frequency signals, and return back to the ground, right? So the low frequency signals which is come from the ground, it is once again magnify and return back to the ground. So while you are going for using the TWTA, so there are different variety of material. This total size of the tube is not more than 1.5 feet. इट मींस 1.5 फीट से भी छोटा होता है ये पूरा ट्यूब साइज में, लेकिन इस 1.5 फीट की ट्यूब में मींस अराउंड 1.5 फीट ट्यूब ना, इट मे बी नियर अबाउट 34 to 35 different category of material working up to 10 to the power minus 9 torr up to 500 degrees Celsius for next 10 to 15 years. That was the complexity, because inside you have to maintain a deep vacuum, ultra high vacuum condition up to 10 to the power minimum 10 to the power minus 9 torr, and there are different variety of material has to be joined simultaneously and meeting the requirement, and it is functioning near about 350 to 400 degrees Celsius throughout its life. And as I mentioned, different category of material like metal alloy, like ferrous, non-ferrous, active material, refractories, non-metals like metallized ceramics and loose ceramics. So there are so many different category of material used on their specific requirement, from thermal point of view, from magnetic point of view, from strength point of view, from temperature point of view. So there are n number of category of material. N means there are near about 35 category of different material used for fabrication of or manufacturing fabrication of such materials, so that it will meet the requirement and do the desired functional requirement as subjected to meet the mission goals. So while selection the any desirable, any tube material, the desirable property basically the high vacuum compatibility. It means high purity, extreme low volatile impurities. It should be less than ppm level, right? Low vapor pressure. It should be less than 10 to the power minus 8 torr up to 500 degrees Celsius. So it should not be actually emit any outgas up to 500 degrees Celsius, and it should be high purity, low impurity, so that any gas like hydrogen, oxygen, nitrogen, or any alkalis like cadmium, sulfur, sodium, phosphorus, it should not be emitted during the working conditions. And physical and mechanical property means ductility, machinability, workability, weldability, breathability, high and low electric conductivity, high mechanical strength, even high temperature, and controlled thermal expansion. These are the properties should be possessed by the any alloy material, especially in terms of mechanical and physical point of view. And material to be avoided while fabrication or the manufacturing of TWT, basically we should not use a porous material, because it may be outgas, and same time it will actually catch the outgas, and after that it may be emit in the future course of action. Loosey and laminated materials, franky and rough surface material, high vapor pressure constitute like Zn, carbon, zinc, oxygen, phosphorus, sulfur. Material difficult to form or machine, and magnetic material with their presence distorted the field. So such kind of material should be avoided while selecting of any tube material. So there are different category of material used in a different process. So I have touched upon those material which is right now used in the space as well as aerospace as well as space materials. And this is what actually I learned through my entire career for up to 14 years of ISRO career, in which 8 years in a launch vehicle as well as 6 years in a payload and space application. But we have the different variety of work right now. You can say changes over during the time. Now we are going for a Gaganyaan, in which we have to select such kind of material which is habited to the human life. It means which is suitable for the human life. It should not interfere to the humans at any point of time. It means it should not be viscous, it should not be toxic, and it should be compatible with the human life, human nature, right? So such kind of material we are selecting. While fabrication also, its fabrication, it should not be any sharp edges, so the damage or any accident should be avoided. So such kind of so many parameters you have to think while designing or selection of any metal, especially for Gaganyaan project. We have air breathing propulsion, in which ramjet and scrapjam engines are there, in which high velocity as well as high temperature materials like cobalt, nickel based alloy we are using, where so that the temperature which is reaching near about 2500 to 300 degrees Celsius, that can be sustained by such kind of material, means super alloy which can be sustained by such kind of material. As I mentioned, re-entry is very tough, so you have to see that the carbon composite or carbon ceramics should be used such kind of high temperature during ascending and descending phase of human space flights. We have the new materials and new development, which is called the shape memory, phase change material, intelligent material. We have the new variety of material which right now in the process. So in future, slowly we are inducting, and we are, you can say, we are merging to the new technology or new type of material we are going to use, so that at present the conventional material right now we are using, we can shift from here to new category of material which comes around phase change material, which is called PCM, shape memory alloy, which is called SMA, intelligent material, which is called IM, or in future it is called maybe artificial intelligence material. So such kind of material also are pipeline to develop, and very soon you can see that such kind of different category of material which are using in aerospace and space sector. And but if you are aware that we are concentrated most on the production activities, so mostly this all development is done through basically Indian Space Agency as well as institution. So the vision which is dreamed by Dr. Vikram Sarabhai is basically harness space technology for the nation development. So we always concentrate to encourage academia, institution, and industry to do R&D, research and development, and to come up with the optimum or the cost-effective solution, so that we can induct such kind of different category of material for our aerospace and space application. So we always try space technology through academia and industry, and we always technology transfer such kind of such kind of things to the industry for the bulk production, so that you can say the FE, foreign exchange, can be saved, money will be there in our indigenously developed capacity building, and the same time we can meet the schedule requirement, and we will generate the generate the career and generate the career options, or you can say employment also through Indian industry. So these are the factor. So what actually new capability, higher capacity, and advanced technology? Right now we are using the space technology, and through academia and industry, we normally build our technology, design, concept, human capital, and infrastructure to build the space technology through the collaboration of Indian institution, academia, research scholars, and through Indian industry, so that the requirement of space technology or advanced space technology can be fulfilled cost effective way. So these are the criteria that right now ISRO is following. These are the actually things that ISRO is following. And anything if you want to develop in material terms of view, so we based on the requirement, mission requirement, application requirement, and functional requirement, we design, develop, and conceptualize the material. We will do some initial trials in the lab level with some small few grams or few kg. We will see its all properties, whether it is meeting the space requirement or it's testing related, environment related, qualification and acceptance related requirements. Once that lab level requirement is fulfilled, then we will transfer this all technology, including that thermal treatment and edging and everything. We will shift to industry and we will go for a bulk production. And based on this bulk production, once again we will test, qualify to meet our surveil or worst case requirement of space requirement, and it is once again fulfill the requirement, then we will induct for our space application. So this is basically a funnel, if you can say research funnel or material development funnel, in which a material started from concept to the final used in a space application. And so that is what actually we learn, we understand the technology, and we are doing for ISRO for last around near about 5 decades. So these are the thing I want to highlight it. I hope now it is 12:30. I hope the most of the thing I can cover you. I try to share whatever I learned through last 14 years. And as I mentioned, these are the snapshot of our activity. The area is basically very vast, and this material area is very, very vast. And it is, if you talk about that, it takes so many hours, even days, to complete such kind of you can say to complete entire material, because one material itself take near about 1 hour. So I have given a small snapshot of all space activity. We start from launch vehicle, right, to spacecraft, to payload, to spacecraft, as well as application. And as Dr. Albert Einstein mentioned, that the important thing is not to stop questioning. So now the forum is open for asking the questioning. I thanks once again to Parul University. Thanks to Ankit, Department of Aerospace, Parul Institute of Technology, Diploma Studies, Ankit, Principal of Diploma Studies, and all the entire staff, as well as those who are listening patiently to me. Once again, thanks to each and everyone. They have given me a chance to share my knowledge, and the forum is open for asking any question. Now, Ankit, it is up to you, Ankit.
Yes, thank you, Ravi sir. We will go ahead and take some time for the question now. Just a reminder, please be sure to type your question to my number 9978225359. I repeat again, 9978225359. It looks like we have some few questions, sir. What is the sounding rocket?
What is a
sounding rocket?
Sounding rocket is basically, you can say, initial or research rockets, in which you are doing a instantaneous observation of a particular atmospheric location. It may be stratosphere, it may be mesosphere. So if you want to get a instantaneous information of the particular desired atmospheric level, so the sounding rocket is the best solution. Just put a payload and it can be go up to 300 to 500 kilometers and get the instantaneous information. So sounding rocket is usually in terms of called a research rocket. You can understand the rocket technology based on the sounding rockets. That's why it is called sounding rocket, right? It is not a misconception that sounding rocket means a rocket which is speed near to sound or exact the sound. It is not like that. It is basically sounding means vertical. It will go to vertical and take the information from the atmosphere instantaneously. Okay.
Second question is, sir, where the rocket or launch vehicles are made?
Please pardon?
where the rocket or launch vehicles are made.
Where ki weather?
Where the rocket
Acha, where?
or
Acha,
launch.
where? Okay, okay. Normally, for a rocket is basically combination of different things. So most of the things, as I mentioned, we used to depend on the industries like L&T, Walchand Nagar, and different industry. They are making for us for a different components. So normally, design, development, everything will be governed by Vikram Sarabhai Space Center VSSC, supported by LPSC Liquid Propulsion System Center Valyamala in Bangalore, tested at IPRC, ISRO Propulsion Research Complex at Mahendragiri, and all the things actually joined together or assembled at Sriharikota, SGS, Satish Dhawan Space Center, Sriharikota, Shah. So, in a rocket, overall, if you talk about that, basically a main leading center is VSSC Vikram Sarabhai Space Center, Trivandrum, but it is a joint venture of all these things, means LPSC, IPRC, as well as VSSC will join together and build a rocket, right? And mostly it is done through Indian industries, from in terms of manufacturing point of view, in terms of fabrication point of view. But if you talk about delivery of material, so most of the Indian industry like Bayforge, Midhani, and different industries which is supporting, which are designing, developing, or you can say making, shaping, or treating such kind of material to develop indigenously to design and build the launch vehicle, or you can say rockets in India. Yes, Ankit.
Sir, is there any life of moon?
Each and everything is actually life. If you talk about Earth, also there is a life. One expected life is there, because after that you cannot survive anything in this. You can say in this era or in this scenario. Now everything has been some life. That life started from some point of view, and it has to be end for some point of view. But we have the still time, enough time to at least we can survive for next 4 to 5 generations. But I have mentioned that the earth is a cradle for mankind, but it cannot be sustained forever. It is told by 50 years back by very good scientist is called Stanton Telescovy, which is basically the father of rocket science. Its simple meaning is basically you are living on the earth, because because of that human life, your existence of humankind, but you cannot sustain the mankind for a long time on the earth. You have to be venture, or you have to be habited to the other planets based on your requirements. Because you see the scenario like pandemic or corona, you see the scenario like Russia, US, China, India, you see the atomic problems, right? So there are a number of problems. You cannot imagine tomorrow what happen. So in future, if you start the working more to habitate the planets or to explore the planet, that may be the solution for the future. Otherwise, you cannot sustain for a long time on this particular earth in present scenario.
Okay. Next question is, what are the different types of fuels that can be used in spacecraft?
Normally for a spacecraft, you are using actually MNO, monolithic fuel, carbon mono or monolithic fuels we are using. Sometimes we are using in a hybrid also, because the reason is even right now we are going for a plasma, nuclear, as well as electric propulsion, but it is in an advanced stage. At present, only electric propulsion we have used in a GSAT, or one of our communication satellite. But normally right now we are using a hybrid and the conventional fuel presently we are using, and it is basically liquid in nature. The advantage of liquid is basically anytime you can trigger in, trigger on, trigger off, means anytime you can switch on and switch off. And the same time when you go to the space, since there is a vacuum, there is no atmosphere, so even our small propulsion, means a small kg of burning of fuel will give the some tremendous speed to go up to the different planets. So that is the main advantage when you are putting a satellite in a space. So even there is no friction environment, no atmosphere, deep vacuum conditions are there, even a small few kg or few grams of fuel will give the very good speed to go up to the different planets. So this is the main advantage. And right now we are using actually some monolithic fuels we are using in spacecraft applications, which is very less in terms of mass. But the main you can say satellite mass is covered by your fuel only, and any satellite life predicted based on the quantity of fuel available in satellites or spacecraft. Yes, Ankit.
Next question is, what is about Gaganyaan mission?
Yeah, actually, that 2 years back, that it means in 2018, 26 January, 26 January 2019 or 18, maybe I forgot 18. Actually, the Honorable Prime Minister of India, that Adarni Narendra Modi ji, has announced that within the next 5 years, it means uh, when it is announced, and it is basically by December 2022, we are able to send minimum 3 or 2 to 3 human nights or UM in the space for 5 to 7 days. Because right now we are sending actually satellites into space, or expandable launch vehicle, means ELV type, which is not reusable, right? It is not can be used for multiple purpose. So we are using that. But now we have to develop the technology which can send human in terms of Indian. I am talking about, means the Rakesh Sharma, Kalpana Chawla, Sunita Williams, they all humans, they all Indians. But when they went to the space, they went to the some different agency from different country. So we are planning to send Indians through Indian Space Agency from Indian soil to the space, and once again safely return back. This whole mission is called basically Gaganyaan mission, or you can say human space flight mission. ISRO already initiated this activity 10 years back, but it is actually full fledged started 2 years back. And hopefully, as per the requirement set by government, ISRO will try to fulfill all the requirement as per the given time slotted or allotted, and we will meet the requirement. And hopefully all the technology we will develop indigenously in India, and try to send 2 or minimum 2 to maximum 3 humanoids in space for 3 to 5 days, or maybe 7 days, and once again return back safely. So that the capability of sending human in space, which is right now available only with US, Russia, and China, so India will be the fourth country to do such things. So it will be the proud moment for each and every Indian, and we will try to do that very very soon by next year.
Next question is, how long can you believe it would take for us to develop a technology like generation ship for interstellar travel to other suitable planets?
क्या बोलते हैं, आवश्यकता है आविष्कार की जननी, अगर नाम सुना हो तो the same thing is also applicable to ISRO also. Once it will decided कि we have to go for interstellar, or we have to go for outside our solar system, so definitely, as I mentioned, कि they already that NASA has did the activity through Cassini. The same way ISRO can also plan it, but till now it is not in the pipeline, or you can say it is not in the mandate. So as such, we are not planning, but maybe in future, if such kind of requirement comes, then definitely we will do it, because as such we never tried. And as I mentioned that the necessity is basically the main mother of inventions. So the same way we will do it for interstellar activity also. Yes.
There is one question. Is privatization in space sector possible in India?
Yeah, it is already initiated. If you see the in June cabinet, this the present government, the government of India cabinet has approved the 100% privatization. 100% privatization means the role of private industry in space sector can be open. It means the unlocking of space sector, and you can say the space activity can be now private players can also come and play their role. It means it is not the autonomous body like ISRO can do everything. Even though now this market is open for everyone, even they can utilize the ISRO facilities. In terms of ISRO facilities, they can utilize it. They can design, develop, manufacture. Even they can use our launch vehicle facility, SHAR. They can launch their own rockets. They can design their own rockets. Now that space segment or space sector is open for each and everyone, and it is actually better opportunity those who are actually going for a new startups. So as I mentioned, government already initiate open for everyone. So those who are going to do something in space sector, so especially in the startup, or you can say new beginning or new industry. So I think space is one of the best or prominent criteria. It's very a huge billion market. So in future you can play a meaningful role. And next 2 to 3 months, it will be approved by the you can say either it will be approved by government through Lok Sabha and Rajya Sabha, and when bill will come like space, you can say space application bill or something, it will be once it will be clear, it will be by by enforce it will be there. So each, for any Indian who is residing in India, even outsider agents also can come and play a meaningful role. Like in US, like Boeing, Lockheed Martin, Airbus, they are playing a meaningful role, and they have joined to hand together with NASA, and they are giving a vital information, or they are giving a vital support to NASA. In the same way, we want that Boeing, Lockheed Martin, Airbus, or such kind of industry should be developed in India. They can join head with ISRO, so the mutual collaboration will enhance our space capability, and we will reach a different sky with a set of time. And we required, you can say, different kind of SpaceX, like Elon Musk. We required so many Elon Musk and SpaceX in India, so that our prestige of nation in terms of space technology and utilization of space technology can be enhanced, because we are almost 10 times to US in population. So if you talk about application, we have the variety of application in terms of space technology, so we have to utilize that. So even one Elon Musk is sufficient for US. So we required minimum 10 Elon Musk is required for Indian continent or Indian environment to fulfill the requirement. So that is what somebody was asked this question. I request at least dream like Elon Musk and do something which is grateful, or you can say fulfill the space requirement in terms of capacity building, in terms of space technology, in terms of launch vehicle, and support ISRO to meet the requirement set by the government. Yes, Ankit.
Yes. Which material is currently trends and research going with the rolling friction welding operation for aerospace?
Rolling friction welding, we normally use the aluminum right now. In the friction welding, normally we are using for dissimilar material. In a spacecraft point of view, we are joining SS304 for titanium, our gas bottle application, and same time we are using AA2219 and I think 2014 for our propellant tank fabrication. So these two actually we are using for our rolling friction welding applications. Yes.
Thank you, sir. Just a minute. On the behalf of Parul University, I would like to present a certificate of appreciation for today's webinar. Thank you, Ravi sir, for accepting our invitation and deliver a talk on the space material with a great knowledge. Thank you, sir.
Thank you, Ankit. Thank you, Palur management. Thank you, each and everyone who is right now listening me. Thanks to each and everyone. And in future, if required, definitely we will meet, right, once this pandemic is over. And hopeful you enjoy the presentation. Thank you once again to each and everyone.
Thank you, sir.
Okay, boss.